I'm Joe Wingbermuehle. I'm a software engineer at Cibo Technologies, and today I will be talking about Scala DSLs and probabilistic programming. So by Scala DSL, I mean domain-specific language. So just as a little outline of my talk, first I'll talk about probabilistic programming in Stan and ScalaStan. Then I'll talk about advantages of doing this in an embedded domain-specific language. And finally, I'll talk about how we do that within the Scala type system. If you have any questions, feel free to stop me at any time. I think we have a small enough group here that I can probably take questions. So, from a programmer's perspective, if I'm given this task of predicting weight from height, and I have this set of data, how would I go about that? Well, it looks like it might be a line. I mean, maybe a pretty poor line, but let's say we try to fit that to a line. So we say that we have weight is some intercept, alpha, plus some beta times your height. And we think that that might be your weight. Of course, it's not exactly right because there's a little bit of error around each of these points, obviously. So maybe we say there's some modeling error or measurement error, and that we model as epsilon. And we say that epsilon is drawn from some normal distribution, centered around 0 with some sigma. And so what we've really done here is we've created a generative model of creating weights from heights. So given any weight, I can give you, or given any height, I can give you a weight that this model predicts. It's not perfect, but it'll do something, perhaps. And we've done this in a completely generative way. I haven't actually done any math to do it. And so ideally, I'd like to just give this to a computer and say, hey, solve this problem for me. This is my model. Give me the answer. And so that's what we would hope to do, and that would be called inference. And so how would I do that inference? So it turns out that there's this really nice programming language called Stan. It's a probabilistic programming language. And it allows you to take these generative models, and it does sampling, and it gives you answers. I really like Stan because as a programmer, this is the way I think. I write my program, and it gives me my answer. It's not like I do any statistical anything. It's just, here's a generative model, give me the answer. I highly recommend checking out the Stan user's guide and reference manual. It's quite comprehensive, and it's about 600 pages. But not only does it have a complete description of the Stan language, but it's also got lots of examples and pitfalls of how to use Stan. Okay, so if we go back to my example of predicting weight, we have our weight drawn. Our weight is some intercept times slope times height plus an epsilon. And we can rewrite that just to be a little in another way that's equivalent with, which is weight is drawn from a normal distribution centered around alpha plus beta times height. And there's some error for each of those points. And so how would we take this and give it to Stan so that Stan could give us the answer for what alpha and beta and sigma should be so that we can use this for actually doing predictions? And so that's what we'll do here. So this is just Scala code to represent this problem. We have our training data represented as n, which is the number of data points. Height is a vector of length n, which is the heights of each person or whatever. Weight is another vector of length n. And then we have parameters that we want to learn, and that's our alpha, beta, and sigma, which is alpha is some parameter. There's a real, beta is a real, and sigma is also a real, but it's got a lower bound to 0 because you can't have a negative standard deviation. And finally, we have the model. So it's basically the same as the math notation, slightly more verbose. Weight is the tilde operator drawn from a Stan normal distribution centered at alpha plus beta times height, and sigma. And This is valid Scala code. It's actually ScalaStan. And of course, we could also add more to this, like a prior, say, if we want to be Bayesian, and say that this is what our prior belief is. So a prior is just, I don't know, like if you're given the absence of data, what is my belief of what the data should be? And the prior tries to capture this. So in this case, we're saying that sigma is probably 0, like we would hope that the error is close to 0. And there's lots of literature on trying to figure out what the best priors are. Stan Wiki has this prior choice recommendations, which really gives you a lot of useful information there. You could run this without the prior, but it'd be less efficient. So it's kind of useful to have a prior. So anyway, we run this program, and we get these results. So we're just saying that we want to substitute our data that we're given, and then run the program, our Stan program, and then we get these results. And this is printing the actual weight on the x-axis and the predicted weight along the y-axis. And we can see that there's some error associated with that, so it's not a perfect model. And of course, if you look carefully, there's actually more than one prediction per actual point. These are draws from the posterior distribution. So this is the really cool thing about Bayesian methods like this, is that it doesn't just give you a point estimate of what the result should be. It gives you a whole distribution. And you can use a point estimate like the best value or the map, but you could also use the distribution to say, well, is it really a wide distribution? Am I really certain of, or am I really certain of the result? And it tells you all that. And of course, there's Thomas Bayes. Okay, so we look at this model and we're like, well, it kind of works, but it kind of doesn't. So what can we do to make it better? Well, in this particular data set, we also have the gender of the participants. So maybe we can make use of that somehow. So how can we put that into our model? And so there are lots of ways you can imagine doing this. This is one of them that I came up with really quick. Just how about a different intercept and slope for each gender? So there's alpha and beta, or 2 alphas and 2 betas. And we're saying that maybe the sigma is the same because, well, maybe, I don't know, there's the same error process for both of those still. Implementing this, of course, is pretty straightforward. You just add an array that has which gender each of the data points is, and then we make each of our parameters a vector instead of real. And then the model is actually pretty simple too. We just say for each alpha, we index it by the gender of that particular point. And that silly little star, colon star thing is just element-wise multiplication. I don't know how many of you are familiar with Scala or Breeze, but that's pretty similar.
What do you mean by element-wise multiplication?
Okay, so yeah, the question was, what do I mean by element-wise multiplication? So beta gender is actually a vector of length n, and height is a vector of length n, and it's returning a vector of length n. Okay, so we run that model, and of course it's a little better, but still not perfect. I mean, there's lots of things we could try throwing in here, doing a slightly different model, say, I don't know, putting some latent things in there, but I guess that kind of gets the point across that it's you can play around with it. It's pretty simple. So that's Stan, or ScalaStan really, but as you've noticed, that's actually in Scala, not in Stan, and I haven't even shown you what Stan looks like yet, so why would we do it in Scala? So now I'll talk about the advantages of an embedded DSL. So I guess first you might ask, well, what is an embedded DSL? Well, it's pretty simple, really. the program is inside, another program is inside the program. So it's like putting a Stan program inside a Scala program. It's simple. So if you are familiar with Stan or in using it in other contexts, like in Python or R, what you do is you take the text version of the Stan code and you reference it in your R code. You can do that either by loading a file or by concatenating strings together. But of course that can get messy, but it's nice that you can reuse the same Stan code in multiple places. Of course, there are lots of advantages to actually embedding it rather than just using string concatenation. For example, I don't know if you're familiar with Scala. How many here are familiar with Scala? Just good. Makes this a lot easier. So a lot of times you will use an IDE. Well, you don't have to, but it makes life simpler, and you can get this discoverability. Like you can, especially if you don't know Stan, you can start typing and you get like all the different distributions that are available to you. And there aren't, as far as I know, there aren't any Stan IDEs. So this is really a nice thing that you get for free by implementing it in Scala. It's type safe, so it would also be type safe to do this in Stan. But if you were loading it from a file, it would give you the error would be in the file that you loaded, or if you were concatenating strings together to build up your program, the error would be in some line number that was meaningless because you were concatenating strings. But if you're using an embedded DSL, the compiler will tell you, hey, the error is right here, and that's actually where the error is, which is kind of nice. The interface is type safe. So in the R world or Python world, you would have to say, oh, I have variable x and it's a vector. But what if you got the name x wrong? There's nothing preventing you from doing that. You could say variable z, and doesn't even exist in the Stan program. But then it just fails at runtime. Here, it tells you that you have to have the right argument. So here, for example, not only do we need to know the name of the argument, but we also have to know the type. So here, we're passing in a 1 for our vector, but 1 isn't a vector, so it's a type error. It's kind of magic. It's composable, so we can build up multiple programs, Stan programs, just by sticking existing ones together. You can do that with string concatenation too. It just gets really messy really quick. Here we have a regression model, and then we have a Bayesian regression model, which is the regression we had before, a simplified version of it actually, and then a normal prior. And then we can just create our final model that's just new Bayesian regression with normal prior. And we can build up all kinds of complicated things like this. We could put priors on the parameters. For example, maybe we wanted a shrinkage prior on there or something, all kinds of things. And finally, we can compute on the Stan model. So this is actually something I'm just starting to play with a little bit more, but it's really cool because you can give ScalaStan your Stan model, and then you can actually do computations on it. For example, optimization. So there's this Stan log sum exp function, which is way faster than this log Stan of doing Stan expa plus Stan exeb. But I don't necessarily know about that when I'm coding it up, and I think it's too ugly to write it this way or something, who knows. But I can write an optimization stage that'll just give this to me for free, which is really cool. You can also do some kind of linting stuff, like if I forget to put a lower bound on sigma, the model will work fine, but it just won't be very efficient because it'll sample outside the range all the time. So hopefully I've convinced you that embedding this DSL is a good thing to do, and probabilistic programming, of course, is awesome. So how do we do that? So the first thing we have to do is stage the stand computations using types, use type members for building complex stand types, and then we use implicits for enforcing type safety, and then abstract interpretation for actually doing linting and optimization type things. Okay, so staging. So the way this works is we have these stand types, which are not necessarily don't necessarily line up with Scala types, unfortunately. So we have, for example, stand int, stand vector, stand real, and our types actually are type members of this other thing that I'll get to later, but you don't actually have to worry about this because it's all type inferred. The types actually is more complicated than that previous tree. They have all kinds of things like row vectors and matrices. And this allows us to do all kinds of cool type checking and prevent problems early on. So to create those, we just do int, and it creates a stand int. You can create an array of ints by calling this apply method on it, which creates a new type that's an array of stand int. And you can do some cool things, type magic with this. So the way this works is we keep track of the type in stand int, and then apologize for all the nonsense here, but lots of type nonsense. Then we just create the array with the contained int. So we can just create arbitrarily complex array structures like this. Clear? Yeah. So then values have some type, so that's the outer part is the value part. So we have a stand data declaration, which is our input to the stand program of stand int, and we create that with data int. Same with parameters. And of course, when we run the program here has like alpha plus beta, that just creates a new stand type that has the right type. So we've gotten to the point where we have all these these values of stand types floating around, but now we want to actually make sure that they're valid because we want to prevent compile errors in stand land. We want to make them show up in Scala land. So, for example, we have this division of a scalar by a vector, and we don't want to allow that. On the other hand, we do want to allow dividing a vector by a scalar. So how do we do that? So if you try to come up with a method signature for divide, it might look like this, but that doesn't prevent us from doing anything. So implicits. Is everyone here familiar with implicits, or how? It's a big, scary concept. I know. It's probably one of the most unique things, I think, of Scala, and I'm not familiar with many other languages that actually have it, if any. They're scary, and I guess not as scary as macros say, but they're very powerful, and it turns out we can make pretty good use of them here. So back to our example with the scalar divided by a vector, we just put this implicit on there. It's another argument list, and it's saying, hey, compiler, give me an implicit that proves to me that I can do this. And so in this case, the compiler is like, that doesn't exist, you can't do that. So it says division is not allowed. You can't divide an int by a vector. So type classes, just a quick walkthrough of the way implicits work in case you're not familiar. So you have a class, my type class T, which is T is the type parameter. And then you have an object, which is the companion object. It's just static for Java people. There's an implicit value my int in there that is of type my class int. And then we can define these functions that take this implicit. And this is an equivalent syntax. So on the first fun, we have, it takes a x of type t. The t will be inferred because it's a type parameter. And then we have this implicit evidence as the second argument list. And we can provide it in the program, but we don't have to. The compiler will fill that in if it can. And if it can, we're able to call that method just fine. Fun2 is just the syntactic sugar for the same thing. And if we call fun4, it finds my int, and everything's happy. If we call fun 4.5, there's no instance of my type class double, and it blows up. Of course, there are other places you can put implicits. I won't get into the whole thing, but this is basically how ScalaStan implements its implicits, or type checking. Okay, so if we look back to our type checking example, here's another one. So we want to say, how does this multiplication work? So we have an x that's a data vector n, a beta that's real, and then we have multiplication that's real times a vector. And we have this implicit multiplication allowed. And we have, here's the definition of that. And then there's actually an implicit def for a scalar and the compound type, which includes a vector. And so that works just fine. Any questions? And that's cool, and this is used all over the place in ScalaStan. There's a huge file that has basically all the rules of how all the different operators work and how the functions work, because this is just a very generic way of doing that. But you can also do other fun things with implicits. So random number generation in Stan takes on a whole different, works differently than in other languages, perhaps. So the way it works is you have a distribution, so normal, and we want to draw random numbers from that normal distribution. And you just do normal 0, 1, and this gives you random number draws from that distribution. Unfortunately, or fortunately, you can only use random numbers in certain places in Stan programs. I guess they kind of want the model to be deterministic. If the model's not deterministic, it's hard to do any optimization or sampling from it. This doesn't make sense. So you can only use this in certain places. In fact, you can only use it in transform data, so that's like before the program runs, it transforms all your data, or in generated quantities blocks, which is like an output that runs after your model has run. So we can use implicits to enforce scope. So our random number generator takes this random number generator available implicit, and then we just have a single instance of this, and inside the scopes where it's allowed to call that, we make the implicit available. And so now when you try to call random numbers from inside a model, which isn't allowed, it says it's not allowed. More uses for implicits. We can check the input data. This has a scary and type signature to it. We have a declaration, so we can set the input data for Stan data declarations, and the data type, it depends on the type of declaration. And so here we have an implicit v, whatever that silly operator is called, t pound Scala type, and that's a type projection saying the Scala type member of t, which is a Seqa double in the vector case. This implicit only exists when that is true. So it only exists if v is a subtype of t Scala double. And in this particular case, we have a Seq of 1, 2, 3, and that is a subtype of t pound double. So it works. Now, if we try to pass the wrong thing in there, we have t is stand double again, and v is an int. But an int is not a subclass of seek of double, and we get a compile time error. So that's cool, and we can get like 90% of the way to proving that all stand programs all ScalaStan programs are valid stand programs, just using these kinds of techniques. But we can't get all the way there, unfortunately. So there are some things like break and continue statements, which are much more difficult to handle. So for example, it looks really scary to perhaps a Scala programmer to see a break statement in a for loop. They're like, that doesn't even exist. What are you talking about here? But it's stand, you can have breaks, and so it's just a function to break out of the loop. But it doesn't work when you're not in a loop. So can we make sure that you only use break statements in loops? And it turns out, well, since we have the abstract syntax tree of the stand program before we generate the stand code, we can actually do that. And so we have this loop checker thing in ScalaStan that maintains the number of nested loops. It starts with an initial state of 0, so there are 0 loops. And then we have these increment and decrement functions to increment and decrement the number of loops. These are actually, this actually uses the state monad, which I think it's kind of cool to show how that works, just because this is a fun application of it, and I don't come up with those too often. It's nice to see, I think, applications of things like this in larger non-toy problems, I guess. So how many of you are familiar with the state monad? So this is not going to be news. That's probably good. Basically, the goal is just to pass around mutable states. Not really mutable, but it kind of looks that way, without having to do it explicitly, because it's really annoying to just pass, oh, updated 1, updated 2, updated 3 through everything. So we'd like to make that nicer. So here, what a state type looks like. It just has a function that takes the current state, and then when you run it, it has a return value and a new state. And basically, the idea is we just build up more complicated versions of that. And then once we have an initial state, once we have the whole graph built up, we can just give it an initial value and say go, and it runs all the state. It runs all the things. And it looks like you're using state. It feels like you're using state, but really it's purely functional and has all the benefits that that has. So our type checking looks a lot like this. We have handle while, which gets called for every while loop, increment the number of loops, handle the while loop, decrement the number of loops. And same for while. And this is just for comprehensions to do this all in the state monad. And then we have the functions that handle break and continue. Break just says, well, what's the current value in the state? If it's 0, then I'm not in a loop. So I throw this exception, and we can see early on that the program's not valid. And then if it is valid, we continue on, and we handle the break. Same with continue. And of course, all this stuff is kind of nasty to implement. The type checking and everything is dirty, but the thing is, once you've implemented it, hopefully your end users don't have to worry about that, and it makes life a lot easier for people down the road. And of course, with this type of thing, it's interesting to think of all the fun things you could do later with optimizing and doing other probabilistic programming type things like non-centered transforms and things that are really tedious to do and stand by itself. So, I mean, that's all I had. Basically, I talked about a simple example of probabilistic programming using ScalaStan, what the advantages of using an embedded domain-specific language are, and how that's implemented using the Scala type system. ScalaStan's open source and it's available there, and Stan is available also. And I highly recommend checking out the Stan user manual. If nothing else, it's very interesting. And if there are any questions, take those. Yeah.
How does your probabilistic code fit into the greater system? What's the end goal otherwise?
The question is, how does a probabilistic program fit into the bigger system? So I guess is that like a question of like how SIVO uses it, or?
Yeah, what does SIVO do, and like maybe how does the system work? If you can say anything about it.
So I can't say. I'm not sure how many good examples I can give here, but we do use. So we have like computer vision algorithms, for example, that look at field, say, and they try to classify what's on that field. And this is one of the techniques that we use for that. And I mean, don't want to get into too many details, I suppose, but yeah, it's used for both learning and running models. So anything else? Yeah.
So how would you have a build system with something like this? So you compile the thing, you have production data, you have test data,
You,
compile it, you ship something to production that has a model.
yeah, so it is kind of unfortunate, I suppose, that basically under the hood what this is doing is using CommandStan, which actually compiles the model. Well, it doesn't compile each time, it caches the compiled models. But when we ship to production, it will actually have, the first time it runs, compile the model. So it will have to have like the CommandStan program and everything available to it. And it runs the model that way. And then we learn the parameters and use the results.
Like a give sampler or something?
Stan uses the nut sampler, the no U-turn sampler, type of HMC. So, anything else? Last talk of the day, very exciting. Yeah.
Is there total parity with the Stan programming language? Can you talk about like how you maintain parity?
So the question is there total parity with the Stan programming language? And the answer is, to the best of my knowledge, I think it is, but it's hard to know for sure. Like I would guess that there are some things that you can do in Stan that you cannot convince the type system is valid in ScalaStan. I think most of the functions are available in both places. I actually just recently added one that was added in a brand new version of CommandStan, so it's difficult to keep up with that, but the base is there, so it's actually not too bad. All right. Well, if there's nothing else, I guess. No, thank you.